Okay, let's wait for seconds for all attendees join our webinar. The attendees are more than 100 now. Okay, I think it's time to start. And first, welcome. Hello, everyone. Welcome to today's class-wide webinar given by Professor Ioannis Savidis. And first of all, let me give a very brief introduction to the distinguished lecturer today. Professor Savidis received his bachelor degree in ECE and biomedical engineering from Duke University and the master PhD degree in ECE department from the University of Rochester. And he's currently an associate professor and the director of the ICE Design and Analysis Lab and the Department of ECE Drexel University. And his research interests include analysis hardware security, machine learning, AI algorithms for prediction and optimization of digital and analog circuits and other circuit design related areas. And okay, without further ado, please join me in giving a warm welcome to Professor Savidis. Hi, Professor. We can start.
Thank you, John, for the introduction. And so wherever you are in the world today, welcome to my talk on these learning algorithms for analog and RF physical design. Before we get into the nuts and bolts of the presentation, I'm just going to quickly introduce my research team, not myself on this case. There we go. So my research team includes 8 PhD students that work on various circuit-related problems. We are very much a circuit design team, basically evenly split between the digital and analog domains. My own interest in the use of ML for circuit design started around 5-6 years ago, and we've been working on applying machine learning algorithms in both domains ever since. I'm not going to spend too much time on this slide, but in terms of research interests, what I've been doing in the last 11-12 years when I started at Drexel, we kind of worked on a few research areas, including topics of 3D integration, which my own PhD work was on, power management and hardware security. And of course, today we are focusing on my team's work in this machine learning driven analog and RF circuit design space. Okay, so here's a general outline of my talk. I'll begin with some background on EDA-based design, describe some ML techniques for EDA, look at optimization techniques, and try to get through as many of the case studies as possible, hopefully all of them, and finally provide some concluding thoughts. So the problem 3 on the first one, I'll probably skip over, and it's a little bit more digital related, but the rest I'll try to get through today. All right, so we know that our standard iterative design process, which often requires ad hoc optimization and multi-dimensional simulations, can result in a single analog or RF block taking months to design, and complex systems even taking longer. So there's not only this high cost, but the design space is also fundamentally limited, given that we often use pre-selected templates. So the question is, why do we design like this? And then looking at the analog IC space, specifically, analog circuits are highly customized across application domains. So we have amplifiers, data converters, transceivers, filters, so on and so forth. And the application domains that require analog circuitry have only expanded in the recent decade. So think something like communication, of course, that we've been looking at, but the automotive segment with all the ICs that go into those, and even bio-inspired computation. So now kind of turning more towards the analog design flow, we can, similar to the digital domain, consider a general flow that includes 5 primary stages. Tasks themselves fall into either almost like a top-down or bottom-up design flow. So the thinking about the top-down tasks, these can include the specification formulation and topology selection and component sizing. Basically design tasks prior to the physical layout. And then the bottom-up tasks, which are typically layout dependent, includes placement and routing. There are additional tasks of interest in analog synthesis, one being that we want to have an accurate estimate of the impact of the interconnect on the performance of the circuit, as there's usually a significant gap between the schematic simulation and the post-layout simulated results. And the second task being the compensation for PVT variation, because temperature, voltage, and process variations often impact reliability, circuit specifications, and the robustness of the circuit. So let's take a look at some of these unique challenges to automate analog design. We saw the list of categories for analog circuits that require high customization to achieve the various functionalities that we want to implement. The additional design considerations beyond the power, performance, and area that we typically evaluate and optimize for digital circuits are what make analog automation more challenging. A set of additional design considerations are shown in the figure, which are for an op-amp, but they apply for other analog circuit blocks. So everything from the amplifier's gain, linearity, power dissipation, voltage swing, slew rate, input-output impedance, noise, component matching, so on and so forth must be considered. And lots of times there's interdependencies amongst these that often result in much greater design challenges. So analog circuits are also more complex with nonlinear behaviors resulting from physics-based effects. So think charge carrier mobility or EM characteristics of the circuit. So, and then what ends up happening is that the design, the performance, and the process parameters are all interrelated. And therefore there are significant trade-offs among these parameters that the designer must consider. So I think in the end is that there should be a better way to design analog and RF ICs. And so the overall motivation of my research team's work is to provide a path where ML can take in target specifications, process design kit, and packaging information, and provide an IC layout that meets the target specifications. And then if we can do that, then we kind of transformed the design space for analog and RF. First, design potentially can be done in days as opposed to months. And second, new topologies can be uncovered beyond human intuition. So in the next section, I'm going to briefly introduce some learning and optimization algorithms that are applied to EDA problems. At a high level, if you're looking at machine learning, it involves training models to learn from data, utilizing a diverse set of algorithms, as shown in the figure. And these algorithms can be classified into supervised, unsupervised, semi-supervised, and reinforcement learning primary categories. Of course, supervised learning, this includes tasks such as regression and classification. Unsupervised learning is generally applied to tasks like clustering and dimension reduction. Reinforcement learning is suitable for dynamic environments and is often used for optimization. And each of these learning approaches offers unique benefits and is chosen based on the specific requirements and challenges of the task that you're trying to actually solve or implement. And the versatility of machine learning algorithms allows them to be applied across various domains, driving basically innovation and efficiency in numerous fields. And this is where machine learning can be highly beneficial for design. So let's kind of look at the role of machine learning in tackling problems in electronic design automation. And the way that I like to visualize this is with a pyramid with 3 levels of ML applications, each addressing increasingly more complex tasks in EDA. And so the first layer that on the bottom is prediction. That basically forms the base of the pyramid. And at this level, ML models are used for the design space are used to predict circuit parameters. For example, we can predict, post-placement interconnect capacitance before actual placement of transistors. This predictive capability helps designers anticipate potential performance impacts and makes proactive adjustments to the design of a circuit. And then at the second level, a more complex task, optimization. Here, ML improves the state of a circuit or its components. So a typical question might be, can knowledge from previous placements enhance the current design? This application of ML supports iterative improvements, refining the design to meet specific objectives more effectively. And then at the top of the pyramid is generation. This is one of the most advanced level. And there's a fine line between what defines generation, but this basically uses ML to create new circuit components or layouts from scratch without relying on existing templates. And then one example could be, can we generate an entirely new amplifier topology with better characteristics than currently available? And generative models at this level propose innovative and efficient designs that traditional methods might not achieve. I mean, we're all trying to get to this holy grail of EDA where we're able to generate novel topologies and designs. And from this pyramid, we see how various tasks align with each other based on the three primary ML applications in EDA. So some tasks such as placement and routing or span multiple levels, while others like circuit verification primarily rely on prediction and optimization. And based on this, we can place the ML algorithms that we saw a couple slides back within the primary tasks executed by EDA-based design flows, with some of the algorithms listed for each primary task. Note that the application of these algorithms is fluid, with some algorithms applicable to multiple categories of tasks. I think clustering being used for both prediction and optimization tasks, or reinforcement learning used for both optimization and generation. So it's not, again, it's a kind of a floating spectrum of where you can use the algorithms within prediction, optimization, and generation. So to this point, we've mostly been talking about classical machine learning, and classical machine learning is fundamentally rooted in statistical methods. This approach heavily relies on domain knowledge for feature selection, making it well suited for basically smaller data sets and simpler problems. Generally, models developed under classical machine learning are more interpretable, which is a significant advantage when understanding the model's decision-making process is critical. And then the shift towards deep learning is largely driven by the availability of larger data sets and the need to solve more complex problems. Improvements in of course, computational power, especially with GPUs, have enabled the training of large neural networks that would have been impractical a few years ago. And deep neural networks are particularly adept at handling large data sets and complex problem spaces. It also eliminates the need for manual feature engineering, as these networks are capable of automatically discovering latent representations. And the primary value of deep learning lies in its flexible architecture, its scalability, and the ability to perform higher order modeling. So deep neural networks typically handle numerical data as inputs. This is a promising beginning, but to fully harness the capabilities of deep neural networks in the context of electronic design automation, we need to explore more complex representations of the circuit. One effective way to do this is through image representations, and there's been a lot of work at using images to represent an integrated circuit. And these images of ICs, they encapsulate the structural information of the circuit, providing a visual context that is rich in detail. And these include predicting physical layouts or classifying different types of circuit components, and even generating new circuit patterns. Here are just some examples of image representations. Some of it, of course, this is for a digital space, but you can see how they're being used to represent clock nets, flip-flops, and so on and so forth. And you can basically extract information out of the primary original image for these. Just as we use images to represent integrated circuits, graph representations offer another effective way to model structural information and connections within a circuit. And these graphs provide an efficient means of representation, often surpassing images in their ability to detail the intricacies of circuit layouts. So in graph representations, nodes can represent circuit components, while of course the edges depict the connections between them. And we use different forms of these graphs, both homogeneous and heterogeneous graphs, to represent our circuits. And this setup allows us basically to include these nodes and attributes as features, and providing a richer and more detailed representation of the circuit's characteristics. However, it's important to note that while graphs excel in representing relational data, they don't inherently maintain positional information, and this is another use of graphs. But this is a spatial graph. That's where spatial graphs come into play. So these not only contain the structural and attribute information typical of traditional graphs, but they also incorporate crucial positional data. This added layer of information is vital in the context of some EDA problems, where, for example, if you're looking at physical placement of transistors or components, you're adding that spatial aspect to the functionality and performance that you're already looking at. All right, and I kind of alluded to this, but we also have these heterogeneous graph representations, which allow us to consider the nuanced features of both device types and even the type of edge connection between devices. In the figure, we have examples of heterogeneous graphs from both the analog and digital circuit space, where you have your gate type, transistor type, and edge type between terminal connections being accounted for. And you can see on the bottom left that is the edges are heterogeneous in that case, and then on the top right and bottom right, those graphs have heterogeneous nodes. So depending on the type of problem you're solving, you basically modify your graph representation to pursue that particular problem. All right, so we'll switch into some of the research problems that we've been looking at. Start with the prediction of circuit metrics at different design stages. First one I'll discuss is the interconnect impedance prediction. So we know that interconnect impedances. Well, actually, I could stop here too. If there are questions on the first part, throw them in the chat window, and I could respond to them. Yeah. So again, interconnect impedance, we know it has a large impact on circuit performance, which typically leads to a large gap between your schematic and post-extracted layout simulation results. So currently, most interconnect models are still analytical. Few ML-based model techniques have been proposed in the last year and a half, but this use of ML has, especially in the last 2 years, has really taken off. So you'll see more and more work in this that use ML techniques to predict and optimize circuits. By applying machine learning, interconnect impedance values can be basically estimated such that the error is reduced between the schematic and the post-extracted simulation results. And these predicted values are useful in guiding further placement and routing of circuit blocks. As a result, the number of simulations required are for parasitically extracted layouts is reduced. Ground truth interconnect impedance values have to be extracted on a layout. However, more accurately predicting the ground truth interconnect impedances during the schematic level implementation of a circuit or after placement provides significant benefit, as corrections and designs can be made earlier in the design flow. That's the basic premise. Yeah, so more accurate post extracted parasitics being brought into the schematic view, so you have a better estimate when you're designing. And so we developed the edge-weighted GNN for early estimation. of post-routing extracted interconnect capacitance values after completing the schematic representation of the circuit and after placement. So we looked at it at two different stages, but this is before routing any of the interconnects. The figure to the right shows the heterogeneous graph representation that is adopted to model the connections between different terminals of a device and net. Specifically, we have the Euclidean distance between pairs of devices, as well as the Manhattan distance. So we looked at two different representations or estimates of the distance between pairs of devices. And those are used as edge weights in the post-placement GNN model, which results in improved model performance as compared to the schematic level model. And you see the actual versus predicted results, and you want basically all those points to be on that horizontal diagonal line. The general architecture of the edge-weighted GNN is shown on the right. The features utilized is dependent on a stage at which we are predicting the capacitance of the circuit. So if we are designing at the schematic level, we only consider the features that are available in the schematic, which include the transistor width, the length, the type, number of fingers. And the post-placement stage, we also consider the Manhattan distance of devices as well as the Euclidean distance of devices as edge weights for GNN aggregation. And so there are a few interesting results from this work. First, the schematic only features do provide, so that's the one on the left. They do provide a good initial coarse estimate of the parasitic capacitance of nets between transistors of an analog circuit. Second, the Euclidean distance between devices actually hurt the performance of the edge-weighted GNN model. So we don't know, maybe the representation of how that distance is calculated is not as good of a representation as the Manhattan distance. And you see on the far right, the third, using that Manhattan distance performed best when used as an edge weight. Okay, so we also did work on analog functional group detection. And so when you're thinking about this, similar to the digital space, in the analog space, we can decompose the layout design steps of design flow into more detailed steps as shown on the right. And by feeding the net list and design rules provided by the PDK, constraints are basically formulated and used to guide placement and routing optimization. And ML can be used for each of these steps. That's the point here, and especially for estimating placement quality and interconnect impedances. And how this relates, well, for analog circuit hierarchies, there's a uniqueness there for to analog design. And when devices can be grouped, they can be grouped based on different levels of functionality. And so when you're looking at this at the device level, in most cases, a transistor can be treated as a voltage-controlled current source. Okay, and then at the subblock level, the analog building blocks are formulated, and this is shown on that right side table. And examples here, include the differential pairs and current mirrors. Basically, the building blocks that comprise unique circuit topologies and encapsulate specific design thinking. And at the next level of the hierarchy, at the subcircuit level, we represent subcircuit components of a system, which can include your operational amplifiers, mixers, VCOs, LNAs, PLLs, and whatever their own subblocks and circuits are. And then there's many others, of course. And then at the top level, we have the design of the system, which includes, as examples, let's say an RF transceiver or data converters. So the question is, from this snippet of a system level netlist on the right, and this includes a netlist for different blocks, are they distinguishable? But can you tell, initially the different blocks are distinguishable, but can you tell which devices are in which functional group? That's the question. For example, try finding a current mirror in the netlist description. And the netlist is what the automated flow of an analog synthesis takes in as input. So the idea is that we need these algorithms to quickly and accurately detect these device groupings, and recognizing these groupings allows for the application of symmetry constraints in device sizing, for example, or placement routing, which is crucial to meet your target circuit specifications. And recognizing the device level hierarchy also enables advanced machine reasoning and ML-based topology synthesis. And we could take this device grouping and use it as an augmented feature for our ML models aimed at basically optimizing downstream circuit tasks. So our group developed this GNN-based technique to identify device groups in an analog circuit. And as compared to a heuristic isomorphism-based approaches, the learning-based model does not require any kind of predefined libraries of circuit primitives. So we begin with taking our analog circuit, which is on that top left corner, it's an amplifier in this case, and converting it into a heterogeneous graph. In this case, the edges represent the type of connection between nodes. So it's a heterogeneous edge type graph representation. And we then use a relational graph stage model that combines relational graph convolutional network principles with graph stage aggregation to capture local topological context per edge type. And once we do that, then we use the node aggregation provided by RSage, by the RSage models to perform multi-class classification. And then finally we look at the bottom, where the scores are in the middle there. We look at the logit score for each pair edge type, calculated for each transistor pair, and take the pairing edge type with the highest score as the predicted class of the functional group label for that given transistor pair. So for in this particular example, when we're looking at which device we're looking, so M1, M2. For M1, M2, the legit score is shown as a 20.65, so it's a current mirror edge type. But note that the pairing edge actually defines the kind of pairing that you have between the devices. And then just an additional note that the VF2 algorithm identifies candidate pairs and initial categories, while the RGCN filters false positives using link prediction scores and preserving category labels for validating these pairs. Oh, yeah, this one shows the predicted one score for each edge type. Okay. As compared to for this work, as compared to prior learning-based work, our model not only identifies functional device groups, but also returns the type of each group as well. And as I mentioned, by recognizing these functional pairing types, then downstream tasks, including placement and routing of these pairs, and even potentially generative models for topology synthesis are provide more detailed information. And when comparing the VF2 heuristic with the hybrid approach we developed, the hybrid approach addressed the high false positive rate of VF2 while also providing the classification of the group pair, as I mentioned. And looking at this, some of the causes of the error that we saw with VF2, again, this is a heuristic approach. It was because devices were connected to a high degree net, so for example, VDD and ground, or devices were sharing some same bias voltage source, or there was an NMOS PMOS connection, and that caused the VF2 to increase in terms of the false positive rate. And this kind of again shows the overall improvement from results of using our hybrid approach. There was an overall improvement in group prediction of up to 14.5%. And of course, as we mentioned before, there was a return of the detected pair type. So they kind of and we have other prediction problems too that we've been looking at, also in the digital space as well. But that kind of gives you an idea of how you can use these machine learning algorithms, and specifically GNNs, to perform some type of prediction that would be useful for downstream optimization or generation tasks. And then the kind of pivoting into generation and optimization of circuits. So the first one that we were looking at is this analog device sizing. And this is in the generation / optimization. So component sizing in analog circuit design is crucial, as we know, to meet the design specifications, and involves adjusting parameters, including the dimensions of transistors and the value of passive devices. This process is typically performed in the pre-layout stage. However, more recently, layout-aware sizing is increasingly being utilized, which basically considers the potential interactions between components earlier in the design phase. So this is where machine learning enhances this process by predicting how design parameters affect circuit performance, including the impacts of manufacturing variations and layout-dependent effects. And this allows for more accurate and effective sizing optimizations, which will lead to robust and efficient designs. So, and then when we're looking at circuit design, treating the circuit as a black box basically means that you're using surrogate models to map from the design parameters to the performance outcomes without needing to understand the internal workings of the circuit component or block. And this method simplifies predicting and optimizing circuit performance, making the design process more efficient. And we can see a comparison of knowledge-based sizing and optimization-based sizing techniques. And the latter produces near optimal results while requiring less manual effort and adapts to technology scaling. And what we have on the right side, this is basically a typical circuit design setup for Cadence Virtuoso, which and we have implemented this in my lab as well. I guess a lot of other labs have as well. But it utilizes a batch mode sampling of circuit performance data, such that the ML models can be trained and used to guide circuit optimization. Oops. Yeah, I gave these bullet points. So, all right. So we developed a sizing technique, V-cult, so for variation-aware classification with adaptive labeling thresholds. It's where classifiers are trained to determine if a candidate solution meets the target design specifications. And these classifiers adaptively adjust their labeling thresholds to enhance the accuracy and effectiveness. The process involves searching for solutions that not only meet the specifications, but they also maximize the robustness of the circuit. And here, robustness refers to the circuit's ability to perform consistently within target specifications across your various operational conditions, which minimizes performance fluctuations across corners, basically. And this method ensures that the selected designs are both specification compliant and resilient, optimizing for long-term reliability. So in this example, we apply the V-cult flow to optimize the multiple performance parameters of a low noise amplifier. Okay, so those are, we start with our design constraints. And then we have 5 process corners and 3 temperature corners that we're considering. And then in addition to the performance requirements, we added constraints on the amount of permitted variation of the performance parameters to ensure the robustness of the design. Okay, so we plotted the standard deviation of the performance parameters across the 15 corner combinations, which is basically the multiplication of the 5 process corners with the 3 temperature corners. Okay. And then the red boxes, these indicate the maximum variation allowed by the specifications. Okay, so any points outside of these boxes have to be thrown out. And the sizing algorithm only looks at and picks points that fall within these red boxes. Okay, and that was the idea and premise of the problem. Okay? So you meet all circuit specifications for whatever circuit you're targeting, and you also are robust across process corners and temperatures. Okay, so we also looked at transfer learning. We're talking about two different types of transfer learning. And this is for basically IC design migration. So we know with technology scaling, a potential challenge and also an opportunity is that we need to port analog designs between technology nodes. So transfer learning is well suited to solve this kind of a problem. So basically, we're taking prior circuit data and models. We're assuming that they're available in the source domain, and then we use that to efficiently apply it to a target domain. And the benefits of applying transfer learning, of course, include faster training, improved asymptotic model performance when the model training stabilizes, while requiring less data than training from scratch. And we can apply transfer learning for migration of designs across circuit topologies or across technology nodes. So if we're looking at what kind of applications you can, and of course, these are research problems, basically, you can apply transfer learning in IC design. These are just highlighting how this approach can enhance different aspects of the design process. So you can look at cross-technology PDK prediction. So utilizing models trained on older technology nodes to predict outcomes on newer nodes basically speeds up adaptation to that new manufacturing process and reducing development time and resources. The other one is a cross-tool prediction. So applying insights from one EDA tool to another improves tool usage and design outcomes. And of course, you can even make these are surrogate models potentially, or black box models. So you could, for instance, do timing analysis when doing it on the digital space, but from one tool and enhance power analysis in another. Or look at the linearity of transistor in one and try to improve it in another. And then you can also do cross-design predictions. So using models trained on specific circuit designs, such as analog circuit blocks to optimize other, let's say, an amplifier or different amplifier designs to optimize amplifier design that you haven't seen. Then there's also the cross-corner prediction, which we've done some work in, of course, that we showed. So adapting models for specific operating conditions, such as whatever temperature and voltage you're looking at, to predict performance across different conditions, basically to ensure that your IC is robust across these various scenarios. And then, of course, the cross-functionality, leveraging data from one functional area to improve the predictions in another. And so all apply to both digital and analog domain. And these are all forms of transfer learning that can be pursued. And in the traditional supervised learning setting, basically you have this independent data that is required for each problem task. In this particular case, this is not showing the transfer learning part. This is just, I have my data sets in each of my domains, and I'm training a model for that target task. But the idea here is that if you're looking at some of the challenges, and we really see this in the analog and RF space, is that data is often costly and proprietary. So acquiring the sufficient data for each circuit task is costly or infeasible. So the idea is to use transfer learning with domain adaptation, where we have a pre-trained model, or you have pre-trained model layers that are frozen. So from one domain, from one data set, and retrained with a smaller data set in the target domain. Okay. So the algorithm involves freezing layers and then retraining the remaining layers using target domain data and repeating until the maximum number of epochs is reached. And what are the freeze layers? These are basically, so we looked at a different number of layers. So let's say you have a 7-layer deep neural network freezing anywhere from 1 to 6 or even 7 of the layers, and then seeing what the effect is on the prediction that you're trying to do. And then the retrain layers, of course, are the remaining layers. For the example that I gave with 7, the remaining layers are trained on the data set from the target domain. And the benefits of this approach include, improved efficiency by reducing computational resources and training time. It enhances performance, especially with limited target domain data, and the adaptability of easily modifying models for new tasks without starting from scratch. The main thing is that you're trying to reduce the amount of data that you need from the target domain. So what we looked at, we applied the transfer performance models for an op-amp. This was from 180 nanometers to 65 nanometers. And transfer learning significantly improves the sample efficiency for circuit performance modeling with simulation-based sizing data, with up to a 50% improvement in the mean average error on test data. So by plotting the test error against the number of training samples, we see a downward trend, which is what we expected. And when you're looking at these two graphs as compared with transfer learning that only requires 100 samples, a standalone training requires 1,000 samples to achieve the same model performance. And so looking at the result on the left, that 0.076. So we needed 100 samples. Because of transfer learning, we needed 100 samples from our target domain, whereas if we train a model from scratch, we needed 1,000 data points from our target domain. And then the figure on the right is that analysis that we did with the different number of frozen layers and how that impacts the prediction of our model. And the interesting thing here is that the F0, there's basically, that implies that none of the layers are frozen, but the initial weights that are determined from the initial domain actually helps in guiding the model to better performance in the target domain. Okay. And this one, the objective is to improve the sample efficiency by using prior design data models again. But in this case, we're looking at topologies and applying our model across these topologies. And if such a transfer is allowed, then we can build a database of analog circuits for training and benchmarking. So what we see at the bottom are two cases where we have on one side a fully characterized analog circuit. Okay, so two analog circuits with full data of the circuit available. And then for the blue box, we have circuits that require prediction of parameters, of which we have not characterized. The idea is to have an ML model where the knowledge is distilled and learned from the already characterized full data, and then we use that and transfer that knowledge to predict for the performance of the unseen circuits. So we considered 4 op-amp topologies for this work. The features that we considered are also listed. These include the transistor dimensions, the transistor type, and a categorical feature that accounts for a gate drain connection if present. And this work also, some of that earlier work that we did on hierarchical device grouping, this work also leverages the device grouping information that we did in prior work. So we explored graph convolution that utilizes again circuit hierarchies, where we included edge conditional layers and also developed this novel circuit GIN layer. And the circuit GIN layer, in a nutshell, is a graph isomorphism network based on some pooling that is trained on a relational graph. And this relational graph encodes the circuit hierarchical information, such as the device group information that can be specified by a designer. And we see from the flow that once a circuit netlist is provided, we formulate the circuit adjacency matrix as usual to represent the circuit topology. Other than that, we also formulate the relational graphs that encode if two transistors are in a group or in the same hierarchy. And if they are connected in a relational graph. And by feeding these relational matrices to a larger model structure, we can actually have different layers learn from different perspectives of the graph structured data. It turns out that the circuit GIN model outperforms the base GCN model. And again, on the graphs, you want all the points to be on that horizontal diagonal line where the predicted and actual values overlap. So for a little bit more detail here, we trained the GIN model to distinguish between four topologies, where the data set consists of data from the four different op-amp topologies. And this model allows for the simultaneous training and prediction of these different topologies that include a different number of features and nodes in each circuit. So again, for the two graphs, the top right figure is the predicted versus actual plot, which indicates the shortcomings of the GCN algorithm itself. You see that it doesn't do a good job learning topological features, and you have predictions that are completely off from what the actual values are. And basically, the GCN lacks the capability to generate different embeddings for different substructures of the graph. And then the circuit GIN is performing a type of circuit recognition that further aggregates based on that group information that we have. And so that predicted versus actual plot for circuit GIN indicates the generation of much better predictions for each of the unseed topologies that are of different size. And so when you look at this, the GNN only model fails to distinguish between the different topologies, while the circuit GIN model outperforms the ECC only models by up to 17% in the calculated R-square scores. And these are the results for when we're looking at different parameters. So we're analyzing the power, the gain, the common mode rejection ratio, the PSRR, and then we were looking at just the GCN, ECC, and then a combination of the ECC plus our circuit GIN, and then calculating the R-square model. Looking at power, all the models do a pretty good job, I would say. There are for gain prediction and even the common mode rejection ratio and even the PSRR, you see that the ECC plus circuit GIN outperforms the other models. So the idea here is that we have transfer learning, which is performed for two design scenarios. So scenario one corresponds to the zero-shot learning, where there's basically no data provided for the target topology. For this case, we only apply the GNN. And then for scenario two, which we call few-shot learning, there's a small data set of 100 points provided for the target topology. And we apply both GNNs and transfer learning for scenario two. So we see four corresponding graphs that are generated for the four circuits that we have. And then that bottom left figure shows the model architecture of the final GNN model that we apply for the transfer. So it consists basically of one preprocessor layer. It's followed by a graph isomorphism network layer, and then two GCN layers. And then we have 8 post-processing layers, which are dedicated to the specific regression task of predicting for the performance. All right, so here are some of the results. So in the table, the negative values indicate lower test errors compared with the baseline ANNs. So for scenario 1, which is the first value of each table cell, GNNs provide a coarse estimate of the circuit performance, and then GNNs trained for scenario 1 result in less test errors than the baseline ANNs for 14 of the 20 cases. Then for scenario 2, which is the second value of each table cell, we see even more improvement. And the fine-tuned GNNs provide an average reduction of approximately 70% in the test error. And we have the root mean square error as compared to ANN models, which are trained with the same 100 points from the target topology. We further characterize the impact of graph similarity on the effectiveness of the transfer. Here we use graph edited distance to quantify the graph similarity. as listed in the parentheses in the table. And we observed that the minimum number of added operations needed to perform an isomorphic transformation from one graph to another, which is that GED score, is lower when the two circuits are similar. And the resulting error is lower for the same scenario. So basically when the same circuit is applied as the test circuit. So the thing here is that similar graph structures and also the distribution of labels between the topologies for training and testing results in a more effective transfer for the model. And we observe on the final row of the table, when all other topologies are used for training, a higher GD score is associated with a higher error value. Okay, so meaning that more changes to the graph are needed to map one graph type to the other. So that you have that in that case, the model performs a little bit worse. And we see that for example, for the three-stage op-amp, this is the most distinct topology amongst the four, and it has a GED score of 45, which is right here in the middle, okay, as compared with the other three topologies. And it correspondingly results in the highest error in testing. I know we're at 9:50. I'm just going to quickly make a comment on this section, and yeah, I'll see how we're going on time, and of course you all can still throw questions in the chat. So looking at RF circuit generation, and these are slides that were provided by Kaushik. So my team is or was part of a team led by Kaushik Sengupta at Princeton that was supported by this first call of proposals from NSTC. So that's the National Semiconductor Technology Center, NetCast, which was basically a nonprofit that was stood up to manage the research and development portion of the CHIPS and Science Act. And the objective of the EDA RF IC program, for the acronym, is basically applying AI methods for the design of RF ICs. And my team's role as part of this team is to develop these forward prediction models for the power amplifier matching network, and use those prediction models in the generation of new passive network topologies or power amplifier designs. Yeah. The idea is to develop an end-to-end RF design flow that's guided by ML algorithms. And the entire process, which is transistor and EM layout aware, navigates through the design space while learning trade-offs between topologies and parameters, and proceeds towards an architecture parameter layout that meets all target specifications. That's the high-level objective for the project. And to accomplish this, there's two things that are done. We universalize EM synthesis, and again, this is some of the work that Dr. Sengupta has done, and as well as the circuit. Then what does this universalizing mean? It means that instead of choosing a template, we choose an arbitrary shape for the passive matching network, and let the algorithm figure out the optimal EM structure for the end ports for the target S parameters. Framing this in this way does two things. First, it allows for generalization. So arbitrary structures can behave as a matching network or combiner or splitter for any end port passive devices. And second, you have this concept of inverse design that Dr. Sengupta has been using that allows us to generate structures beyond what human intuition comes up with. And there's no templates for a given specification either. So we can invent new circuits that do not exist. And this framing also allows us to universalize RF IC design. So instead of choosing fixed pre-chosen templates, one can imagine RF ICs to be a complex combination of inverse design passives and active devices. And the AI needs to figure out the active components and the passive components, their structure, their parameters, and so on, such that the target specifications for the circuit are met. So Kaushik's group has used the proposed ML models that estimate EM fields of these pixelated matching networks to design RF ICs, which they measured. The ICs include a broadband millimeter wave power amplifier covering the 34 to 70 gigahertz frequency range, and a second one that is 110 gigahertz another 110 gigahertz power amplifier with specifications shown in the table. So for the 110 gigahertz design, they have a common emitter stack. The intra-stack inductor has been manually replaced with a transmission line length, and then they use the inverse design, so the their own ML models for the design input to design the input output and interstage matching networks, and then the common base driver provides the extra gain. I don't know if I have time, but the main thing that I wanted to say here is that there are obviously there's a big aspect of data sets and the lack of standardized data sets, more so in the analog space. There so and the big thing, of course, is that there's proprietary data, and EDA tools themselves are proprietary. So, you know, if you're actually comparing, this is a tool, but if you're comparing on proprietary tools and trying to use those as openly share or benchmark data, that's prohibited, and you run the risk of losing your academic license. So the main point here is that I wanted to make was that there are tools. I talk about Align and Magical in the slides, one coming out of the University of Minnesota and the other one from Texas, Austin, and then there's BAG out of Berkeley. My own group has been using open source tools as much as possible so that any kind of data set that we do generate, we are able to distribute. So that's on the tool side. On the this is the Magical. On the PDK side, there are open source PDKs, which I've listed there, and we've been using these. And of course, there are closed PDKs that we also have access to that we could develop models for, but of course, those are not. They have to be scrubbed in a way to be able to release that kind of comparison and data. But you won't release the data directly. It's more like a comparison or the analysis that you're doing based on some kind of machine learning model that you've developed. Okay. The IHP 130 nanometer is probably the one that's probably most relevant to this audience. That one's a BiCMOS process. It's I think it's German or European based PDK that's I would say semi-production ready. So that's the one that we've been trying to kind of expand and look at for analog and RF based models that we're developing. And I have this whole other section on standardization of ML models and such, but I am going to skip it for now. I'll see if I can make the slides available in some way. As a note, I did give a tutorial presentation at ISCUS this year, and those slides are also, there's some material here that's not in that one, but those are also available on my website as well. But to give some time for questions, just a couple thoughts here, conclusions. Machine learning is transforming analog digital EDA by enhancing efficiency and expanding capabilities. It significantly reduces the need for repetitive simulations, and which basically speeds up the design process. And ML not only enables a more thorough exploration of the design space, but also predicts potential issues such as if you're looking at parasitic impedances or and variability early in the physical design flow, which basically helps in making informed decisions and reducing the costs for design that are caused by iterations. Currently, ML is used to refine and improve traditional heuristic methods in EDA, and allowing for a more optimal and efficient design in less time. However, traditional heuristics and procedural synthesis will still dominate, I would say, the latest tools. And again, there's still a lot of potential for greater integration with ML techniques, and that's what you're seeing currently. There's all the primary EDA companies are pursuing this. There's a lot of work of integrating they're not going to get rid of their heuristics anytime soon, but looking at ways to enhance their heuristics, their traditional heuristics they've developed over the decades with machine learning techniques. And it could also just be for providing some kind of suggestions for the design that you're looking at. And then looking ahead, the future of ML and EDA, it looks very promising with potential developments toward direct generation of designs through generative models. And that's where we want to get to, being able to directly design or create designs with generative models. And that's down the road, but that's what we're all working towards. I have a list of our publications that a lot of these slides are from. And thank you.
Thank you, Professor Savidis, for your insightful talks. And we still have some time for Q&A, and the audience are welcome to raise your questions using the Q&A button in the bottom of your window.
There's someone that's raising their hand. Alex, okay.
So Professor Savidis, can you see the questions in the chat box?
I think he wants to verbalize the question. So is there a way to turn on the mic or not? For the attendees?
For the attendees, if they raise their hand, they can
unmute.
Yeah, anyone want to?
Oh, there's 3 questions. Okay, can you all unmute?
Let me see how to unmute.
Okay, Alex, I think you could ask your question.
Hello.
Yes.
Audible?
Go ahead, Alex.
Hi. Professor, just had one question. Can you share this PPT slides as well as the recording of this for my reference later on?
I believe Cass will be sharing the recording.
All right, that's great. Yes. Thank you, Professor.
Dennis?
Can you hear me?
Yes.
Oh, okay. I'm curious, did in your research, has your tools developed any novel topologies for analog circuits?
So that is the space that we're working on. We're starting with power amplifiers. It's the tricky part is that the topology, so we can generate topologies, but and we throw away a lot of them because there's connections missing and so on and so forth, right? And we're trying to use some kind of like a LLM based guidance for what kind of topologies to generate. But for power amplifiers, for example, right, the topology itself is not the most important part. So the biasing conditions and sizing that make that give you the class type. So there's still. So you can have the topology, but you need that second aspect, which is, I think, a little bit more critical when you're designing, like, for example, the power amplifiers, the biasing conditions, and whatever the variability conditions or constraints that you have that you need to design for.
Okay, I believe that.
Yeah. So yes, we generate, but there are other algorithms that have to run on top of it that need to be executed to make sure that you meet the constraints that you have. And specifications.
Thank you.
Giovanni?
Hi, can you hear me?
Yes.
Okay, cool. I have a couple of questions. One is NANDGate has a open source 15 nanometer standard cell library in addition to the 45 nanometer library you used. May I know what's the reason for not using the 15 nanometer standard cell library?
Wait, the 15?
Yes.
That was open. NCSU, is that the NCSU one? I can't remember. Is that the
No, I got it from the NANDGate webpage when they first released it. It was before the Sivaco or Simucat acquisition. So it was like a long time ago.
Yeah. So it's we have the ASAP 7 one that we use.
Okay, cool.
We use the advanced ones, but yeah, there are definitely and I'm trying to find that slide, but there are definitely different PDKs that are available. Just go back to that. That are open.
Yep.
Yeah, I think it just depends on what the data set. But this is another point of interest because if you want like a data set that's available made public, I almost feel like there needs to be some kind of structure on how we approach this, and even the formatting, which I didn't get to talk about too much, but like a schema representation of the data that you have that allows for an interchange of schematics and layouts on these open source PDKs so that we can progress in the in developing whatever algorithms that we need to develop in this machine learning space for whatever kind of prediction or generation that we want to perform.
Okay, and then can I use? I know that meta learning allow us to like use different kinds of machine learning algorithms to do something. Can I use something similar like a meta algorithm for portfolio optimization of machine learning techniques or optimization techniques to do like analog or RF IC design automation?
What? Wait, you said which you said meta?
Yeah, meta learning or meta algorithm. So like,
Okay. Um, okay. So how do I want to answer this? So generation is interesting. So you should theoretically be able to, but as mentioned, there are pitfalls in some of the implementations here. So especially in the analog and RF space. But I don't this is an active area for the generation component. What I've seen is the use of LLMs for at least topology generation. But the optimization aspects, that is not an optimization, meaning like sizing, even haven't even talked about the physical aspects where I talk about the placement of devices and how to optimally place it automatically with machine learning algorithms. But I would say meta algorithms are being looked at, but it still has to be that you're meeting constraints and you're not. No, it's not just like the topology and that's it. There are aspects obviously that you have to uh, optimize the circuit for.
okay, cool. Thank you. One last question. Can
Sure.
I port the techniques for analog or RFIC EDA to be used for silicon photonics or optoelectronics?
Okay. That is a good question. I'm not sure because theoretically you're developing these surrogate models based on data that you have on a particular process or flow. So whatever the EDA tools are that you're using, that also impacts your surrogate model. And there's work that's being done to like, so maybe there are aspects of the optical circuit that these surrogate models could work on. But my first inclination is that if you don't have data that's representative of the problem that you're looking at, then the models are not going to perform correctly. But maybe there's a transfer learning aspect there that you can theoretically use some of these RF models and train with a smaller subset of data in the target domain if there's some kind of a relationship. Like the data that you have in the source domain has to somehow represent the target domain. If it doesn't have that, then I maybe the model itself could work, but you would still need to have data from that target space.
Okay, cool. Thank you so much.
Yes. Ming-Jean?
Can you hear me?
Yes.
Okay, thank you. I am just working a lot of machine learning for the uh, digital circuit, but I'm just new for the analog. And I have a question that is just about the data set. I find that it's really hard and will take a long time using just like the line to run a circuit from the front to the end. May I ask about will there be some of the data set that is just clear and um, completed by others and open sourced for us to do machine learning or something else?
Yeah, and so okay, the last part of my presentation was kind of trying to touch on that aspect and what's needed. I didn't get to cover that last section on you know some of our schema work in the digital space, but the idea here, and again, this is in the digital space, but the principles apply to the analog RF space, and we're actually expanding this concept that we have for analog and RF. But the idea here is that right now there's probably a lot of duplicative effort because everyone's trying to create their own data sets, and of course there's only a limited number of open PDKs, and then RF and analog. Okay, digital, there's a whole flow in place. Open road is there. You can kind of have a tool set. You can generate open data. Magical and the line are there, which I brought up, but they're not as developed and supported as open road, right? So it makes it a lot more challenging in the RF analog space to generate data like you mentioned. What we have internally is these ocean scripts that can quickly generate data, and then we take that. It took us a long time to get Magical to work, but we got Magical to work now. It's a LVS clean, not necessarily DRC clean, but LVS clean, and we can generate data pretty quickly using that. But I'm actually with you. I think being able to put in some kind of a format and structure that can be used across different research groups to make it more accessible should be a objective of the research community.
And when I am working just on the digital circuit, that I only need to focus on the PPA, such as performance and power and area. But when I get to know about the analog circuit, there are a lot of performance metric, such as if you have different functional for this circuit, it will have different ways to judge this circuit will performance good or not. So
Sure.
that makes me feel a little confused about what should my model just try to predict. It's about the power or something else, or just for each kind of the functional, I need a model that can help me to predict it.
Okay, so there's a lot of points to be made here. So yes, so whatever your target performance specifications are that you want to design for, you have to extract data or simulate data and have a data set for, and your model has to be trained, and that model also is unique based on the type of problem that you're trying to solve for. Now, the thing that you would want to do is you would want to have a generalized model that doesn't. So it shouldn't be that you have a model for each type of specification or performance that you're trying to basically create a surrogate model for. So you would want it to be a generalizable model that, at least for, let's say, I don't know if you're looking at bandwidth or linearity or gain, whatever those parameters are, you can account for them in the model that you're generating. Sometimes it doesn't work, so you have to have a target model for each of the specifications. But in general, my point would be that you would want to select or develop the model on whatever it is, neural network or whatever kind of model you're trying to generate, to be generalizable enough where it accounts for the parameters that you're most interested in. performance
Well,
parameters you're most interested in.
okay. Thank you so much.
Hyungjin? Yep.
Okay,
Go ahead.
can you hear me?
Yep.
Thank you for the great seminar. I have two questions about grouping transistor from a netlist, such as a current mirror you showed earlier part of this seminar. So how many training data are required for training the networks? And the second question is, how do you label all those training data? It's not related to the circuit performance, so I guess the circuit simulator cannot label them automatically.
Yeah, okay. So for the that's for the grouping work. Okay, so for the grouping work, we had it's a much smaller data set. It was 10, hold on, let me think about it. 10 circuits with whatever number of nets that each of them had in pairs that they had. So I think it was a total of 180 or 200 different types of pairs that we were looking at. And then those I had a summer intern label them.
So basically, it's all manually labeled.
For now, for that work, it was initially.
Okay.
Yes.
Thank you, Professor.
Giovanni?
I'm wondering if it's possible for you to work with Professor Andrew Kang from UCSD to create like a ML EDA Commons, just like ML Commons, but for EDA, such that students and EDA software developers can access the information, not just like companies and famous professors. As long as like the thing is subject to US export control laws and those of the EU, like I would like to see that happen so that the students can have a better chance of doing the work, replicating the work too, including for course projects, not just for publications. And then can you also organize like ML for analog or RF EDA research contests for like conferences like DAC, ICCAD, MLCAD, AICAS, so that the students can compete and collaborate? Thank you.
So, interesting point. Yeah, there's obviously a lot more infrastructure on the digital side. And the interesting thing is that I was on sabbatical last year in working with Andrew at UC San Diego. So yes, there is definitely a pathway there to discuss that with him. Contest competitions, that's it's very useful. I think okay, so you start with some, I guess, a nice target problem, that maybe an initial problem that we maybe just get our feet wet in the competition space. But yeah, I'll definitely consider both. Or I guess it was 3 suggestions you made, but I'll consider all the suggestions. All right, I don't see any more questions. Thank you all for staying
Okay.
on.
Yes, thanks a lot for your patient answering all the oral questions. And maybe there are still some text questions, but due to the limitation of time, I suggest if any audience still have questions, you can access the classified webinar web page, and you can send emails to our distinguished lecturers, Professor Savidis.
Thank you, John. Thank you, Samantha.
Okay, so I think this is the end of today's webinar, and look forward to see you in next round webinar activities. Yeah. Thank you, Professor.
Thanks.